Welcome to our unit on chemical reactions. Now, this unit is one of my favorites because in chemistry, there's one thing that we've been waiting to do all year, and that's grab some chemicals off of a shelf and throw them together inside of a beaker and just see what happens, hopefully creating some sort of a chemical reaction. And that's exactly what we're going to end up doing in this chapter, but with a little bit more finesse than just that. What we need to do is to develop a system of rules for some safety, of course. We want to make sure that we have a way of predicting whether or not that chemical reaction is going to take place, and if so, could it potentially be dangerous, so that we can make sure that we're nice and safe as we actually start to throw these chemicals together on the inside of a beaker. So in this first section, I simply want to talk about what is a chemical reaction, and specifically, how do we write that down? Now, you may specifically be thinking about a chemical reaction, at least in your mind, something more like this. And of course, this is exactly what we would be looking for. These are kind of some extreme examples of what chemical reactions can be, but still, this is kind of, I think, what most people have in their minds about when you see a chemical reaction, what actually may end up taking place. Now, don't forget that inside the lab, there are four visual qualitative signs that a chemical reaction is taking place. And they include a color change, the formation of a precipitate, and don't forget that that's a solid that forms when you combine two liquids. It's almost like a magic snow that occurs on the inside of your beaker. A change in heat when you are neither cooling the beaker nor heating the beaker forcefully. So you pour two room temperature chemicals together and they suddenly get hot. That would be a change in heat. And then finally, the formation of a gas, which we would perceive as being some bubbles. Now, all of this is well and good. We can see visually in the lab when a chemical reaction is actually taking place, but we have an additional problem. We're going to need to report this out on paper so that we can communicate what we have seen to other scientists without actually doing the chemical reaction in front of them one more time. So you may have seen something that looks a little something like this. Now, this is a stripped down basic version, but you may have seen something that looks like this. This is what we would call a chemical equation. And this is what we would write down in the lab, in the classroom, to describe a chemical reaction that we have just seen. And there's a couple key components to this chemical equation. First of all, the most key component is the arrow that's in the center. Now, the arrow that's in the center communicates a very key piece of information. This indicates the transition from one form of materials to the other, and that directionality will show you where you start and where you end. Now, oftentimes, this is a way of communicating a word, an idea. So we can actually translate the arrow into a couple different English meanings. For example, if we would be simply saying this sentence, this is almost a chemistry sentence. If we would be saying it in English, we could substitute the word makes when we hit the arrow. But what would just work just as well might be something like yields or produces. Any of these would absolutely be fine. My favorite is reacts to form. I think that just sounds really, really fancy. Now, the arrow separates two key sides from this chemical reaction. Where you've started, and that's highlighted here in red, the A plus B. The materials on the left-hand side would indicate the reactants. Now, the reactants are the starting point of the chemical reaction, and this is often what the chemist will actually put into the beaker. These are the chemicals that you'd be grabbing off of the shelf to actually start the chemical reaction. And of course, the materials that are on the right-hand side, well, this is what ends the chemical reaction. These what would be called the products of the chemical reaction. This is what a chemist will get out of the chemical reaction at the end. Now, I just wanted to be clear that there are some additional symbols that we can use with a chemical equation. And these additional symbols do communicate an additional level of information. For example, we have this cute little triangle written over top of the arrow. That would actually indicate that this reaction only occurs when it's heated. That little triangle is called delta and often indicates that we're heating the chemical reaction. You could also just simply have a chemical formula over top of the arrow. Now, this material would neither be a reactant nor a product, but yet is necessary to make the chemical reaction go. We're talking about a catalyst. So catalysts, because they're neither reactants nor products, are often written above the arrow. And we'll just write the chemical formula for those right over top of the arrow. Oftentimes, you'll often see this as well, this ATM, which is short for atmospheres. This would mean that this reaction occurs only at a specific pressure. Or something more familiar, 250 degrees Celsius, this would indicate that this reaction only happens at a specific temperature. There are also these other really weird little symbols that you can write after each and every reactant and each and every product. Notice that they're S and L and G and AQ. What we call these symbols are state symbols, and they indicate what state of matter that each one of these materials has been in. Now, if you want to use in parentheses, notice they're always in parentheses and they're written down low like a subscript. If you use an S, that indicates that your material is a solid. L, lowercase l, indicates that your material was a liquid. Lowercase g indicates that your material is a gas. And my favorite symbol of all, AQ. AQ indicates that the material is aqueous. Aqueous, that's really weird, I know, but aqueous simply means dissolved in water. And notice in our equation here, do you notice, is water part of the reactants or the products? No, it's not, and that's okay. Oftentimes, chemists will put chemicals into water so that they will collide more frequently. And we'll talk about that in just a moment. But again, unless water is specifically actually reacting, which means it's going to have its bonds broken and then reformed later on in the product side, we do not put it into a chemical reaction. It's simply like a place to do the chemical reaction inside of. It holds the chemicals close to each other. So why though? Why don't we write water in here if water is going to be part of this chemical reaction and necessary to get it done, but not specifically reacting? Well, chemists know that anything that can make the particles on the inside of this reaction collide more frequently, that the reaction will speed up. In order for the chemicals to react, they need to come in contact with one another. They need to collide. Now, that includes a variety of different things that we can do. That's often why we stir a chemical reaction while it's happening, because it often gets it to go a little bit faster, or why we might use stronger, more concentrated chemicals, or why we might heat something up, or crush up something and increase that surface area, or finally even use a catalyst. All of these items will speed up a chemical reaction. But the most important thing that you can do, again, is to get those particles to collide more frequently. I just kind of want to show you what this actually looks like. This would be the effect of temperature on our particles, and often why increasing the temperature of a reaction can get the reaction to go faster. Now notice here, I'm increasing the temperature of the particles on the inside of this container, and what happens to them? They start to move faster and faster, and because they move faster and faster, they collide more frequently. And each one of those collisions, a chemical reaction is possible. Notice again, when the temperature starts to drop back out, the particles slow down, and now they collide less. So less and less chemical reaction would be possible. I just kind of wanted to show you this image as well. Oftentimes when you're dealing with a solid, which is pictured at the left, there's very limited space for those collisions to take place. Those little red particles literally have to bounce on top of the surface of this very large cube to try and get a chemical reaction to occur. But if we crush it up or dissolve it in water, which is even better, notice that the surface area increases and the two chemicals can mix better now. And when they mix, they can collide more frequently and therefore speed up the chemical reaction. So again, just one more time, dissolving the chemicals in water essentially is the same thing as breaking up a very large solid. It increases the surface area and allows the chemicals to mix. And anything that allows those chemicals to mix better and better will speed up the chemical reaction. Water does not necessarily have to be a chemical reactant. So you're going to see often in this particular chapter the little state symbol AQ. And again, AQ means dissolved in water, but that water is not necessarily directly involved in the chemical reaction. It simply pulls those chemicals close together and allows them to collide more frequently.